students, so welcome back to the second class one shot video for your chemistry class in Masterstroke series. So here we are going to discuss the entire chemical kinetics chapter up to the KCET level. We will definitely start from the board level and then consequently we will move to the KCET level, and this entire series definitely is going to help you to boost up your conceptual clarity. And please while watching the video make sure you are making a proper note, because this note is going to help you out during the 11th hour of your preparation. So yes, without further delay, let's get started. And one more thing that I really wanted to tell, that please ensure that you have enrolled yourself in the most awaited test series that is given by Deeksha Karnataka ABHYAS KCET test series to check your eligibility, not eligibility, rather where you are actually standing right now, because this particular series will give you 35 mock tests, along with that all the PYQs from the all chapters. So without further delay, please enroll yourself and keep practicing. So yes, without further delay, let's get started. So in this particular chapter, kinetics, what we will actually study, you can see first we will study the rate of reaction, then factors affecting the rate of reaction, then we will study the rate equation, then we will proceed with the effect of concentration, methods to determine the order, effect of temperature, effect of catalyst, and at the end collision theory. So these are the sort of things that we are going to cover in this particular session. Okay, so definitely I will focus on the most important target zone that actually you are going to face in your board examination, definitely, as well as repeated year question came in the KCET from those target zones only. Yes, so let's proceed. First we will start from the rate of the reaction. So here you can see that can be determined in two ways. One is average rate, another one is instantaneous rate. And then we will proceed with the differential rate equation. Okay, so first, whenever we are going to discuss about the average rate and instantaneous rate, what does it mean? So here you can see whenever it comes to the average rate, it is a measure of the rate or the time that is needed to complete a certain amount of product at a proper interval of time. Means, let's say I'm talking about 1 minute. In 1 minute, how much reactant will be considered? I mean consumed. Okay, that is your average rate. Okay, and it is represented by delta. This particular interval is measurable. Means it's not very small that you can't even define, or it's not too large. Okay, it's a measurable quantity. Okay, that is measured in naked eye, like 1 minute, 2 minutes, like that. Okay, but whenever it comes to the matter of instantaneous rate, it is measured at a particular instant of time. Okay, reaction is going on, but for a very small instant of time, 0.003 seconds, like that, very small instant of time, if you want to find out the rate or that particular time, very small duration, very small interval, right? Those cases we use the instantaneous rate, and here we use the DDT, means differential change. Differential change means the way you can think it's even smaller than that, right? Very small change. So why to proceed with the instantaneous rate? Because it will give you the more precise value of the rate, right? A particular instant, right? So I guess you understood the difference between the average rate and instantaneous rate. The concept is very important here. We will definitely proceed with the instantaneous rate. As I told you, it will give you the more clarified vision about the rate of a reaction. Okay, I guess it's clear. Let's proceed. So here you can see two different type of graph that will represent that how actually you should find out the average rate and instantaneous rate. So for this particular case, here you can see concentration of the reactant with respect to time. The graph will be something like this. Why? Because with time, the concentration of the reactant, let's say I have started the reaction with A and B. With time, the concentration of A and B will decrease. So that's the reason the graph looks like that. Okay. So now here you can see I am having T1 and T2. Okay. So during this particular time lag, I want to find my rate. So T2 minus T1, that is the delta T. So I have to find my rate within this time zone only, right? Within this time zone only, right? That will represent the average rate. So you can see it is a considerable amount. You can see it's a considerable amount, this much gap, right? But whenever I'm telling exactly at this time, you can see here T is written, exactly at this time what is the rate? How will you find out? I will just draw a straight line over here that will touch the curve here. Here I will just draw a straight line. Okay, I will draw a slope out there, right? So then I will calculate the slope, right? So that will give you my instantaneous rate. I guess it's clear to you. During this interval, it's a measurable interval, considerably large amount of time. In this particular time range, what is the rate? That will be calculated using this, right? This particular equation, R2 minus R1, like that. But whenever I'm asking at this particular time, not a range, at this particular instant, what is the rate? So here just put one straight line where it will touch the curve, there you draw a slope, right? Then calculate the value of slope, right? How to calculate? dy dx, right? What is there in the y-axis? Concentration of reactant, that is the concentration of reactant by dx, right? And y minus, because concentration of reactant decreases with time, that's why the minus sign comes. Okay, so that is nothing but the negative of the slope. I guess it's clear to you. Let's proceed. Here you can see this is a product graph. Okay, again same thing but with respect to the product. Okay, so product, as you know, with time product will increase, right? Here you can see from initially it was 0. As the time will go, the product will appear, right? That's the reason we put one positive sign, slope will come as positive. Okay, again in this particular time zone, T1 and T2, if you want to find out the rate of the reaction, that will give you the average rate. Okay, average rate with respect to the product. Okay, this is this one, you can see delta P by delta T, average rate, P2 minus P1 divided by T2 minus T1. Got it? Now exactly at this instant, you can see here, exactly at this time, what is the rate? So I will just again draw a straight line. It will touch here. Here I will draw a slope. Okay, I will draw a tangent. Okay, and I will just calculate the slope out there. Okay, so if you calculate the slope, you can see you will get dy by dx. What is y? The product concentration. X is time, right? That is the slope. Okay, so instantaneous rate is nothing but the slope of the particular point. Okay, if you draw a tangent out there, the slope that will come, that is the rate itself. Okay, and plus sign y, because the product will appear with time. Okay, I guess this thing is clear to you. Okay, so this is the graph with respect to reactant, this is the graph with respect to product. I guess this thing is clear to you. Okay, let's proceed further. Okay, one problem is there, let's solve it. Which of the following statement is correct? The rate of a reaction decreases with the passage of time and the concentration of the reactant decreases. Definitely it's going to be the correct one, because just now I showed you rate of the reaction decreases as the time is passing, because the concentration of the reactant is decreasing. Okay, so definitely option A is going to be the correct one. You can go through the next options as well, you will understand that they are actually wrong. Okay, so let's proceed further. Okay, so differential rate equation, how actually you should write. Okay, so basically let me just show you. If you want to write normal average rate equation, normal average rate, okay, let me show it here. Let it be 2a plus 3b will give you 4c plus 5d. Okay, This is your equation. How you should represent this? You should represent the rate of reaction. ROR indicates rate of reaction. How you should indicate? How you should represent? I am showing you average rate. Okay, you should use delta sign, right? So that is nothing but, see, here you can see the stoichiometry that is coming, okay, that should be that should go to the denominator. Okay, why this? Because you are doing it with respect to 2 mole of A, but I need the rate with respect to unimolecular 1 mole of A. So how we should do? 1 by 2, like that we do na. 1 by x, let's say x mole is there, so 1 mole with respect to 1 mole, how we do it? 1 by x, right? That. So that's the reason stoichiometry is divided. Okay, so and one minus sign comes, it represents the reactant will disappear. Okay, the negative sign implies that the reactant will disappear. So 1 by 2 delta concentration of A by delta T equals to, again, minus 1 by 3 delta concentration of B by delta T, right, equals to, here I will do plus because product will appear with time, right, plus 1 by 4 delta concentration of C by delta T equals to 1 by 5 delta concentration of D delta T. This is how average rate needs to be written for rate of reaction. Now let's proceed with the differential rate equation. So whenever it comes to the differential rate equation, nothing, just del will be changed with D, that's it. So rate of reaction for the given equation, you can see this is my reactant, these are my products. So reactant will disappear, right? So here we can write 1 by 2 minus 1 by 2 D of concentration of N2O5 divided by dt, right, equals to 1 by 4 plus 1 by 4 D of concentration of NO2 by dt equals to, see here no stoichiometry, no need to write anything, D of concentration of O2 divided by dt. This is how you should represent, this is rate of the reaction. Okay, one more thing I just wanted to tell you, that is rate of appearance. Okay, in short we will call it ROA, rate of appearance. Okay, how you should represent the rate of appearance? Who appears in the reaction? The product. So rate of appearance, whenever you are mentioning, then it should be with respect to product only. Okay, so rate of appearance, let's say rate of appearance of NO2. Okay, then you should write only D of concentration of NO2 by dt, like that. Plus minus nothing, definitely by default plus is there. Okay, remember for this case, whenever you are finding out rate of appearance or rate of disappearance of something, then don't put the stoichiometry. Okay, only the change in concentration with respect to change in time. So here what you have to remember, no concentration term should be included. No concentration, sorry, no stoichiometry should be there. Okay, whenever they are asking for rate of appearance or rate of disappearance, there should not be any kind of stoichiometry or sign. Okay, but when they are asking the rate of the entire reaction, then go ahead with the sign and with the stoichiometry wala fact. Okay, next if I write rate of disappearance, rate of disappearance. Okay, who is disappearing here? Definitely reactant. we will call it ROD. Okay, here of N2O5. Okay, how you should write it? Definitely D of only concentration of N2O5 divided by dt. That's it. No stoichiometry, no sign. No stoichiometry and no sign. Okay, I guess I could make it clear to you. When they are asking the entire rate you write, then you can proceed with the sign as well as the stoichiometry. You have to divide with the stoichiometry. I told you the reason. You have to find the rate with respect to unimolecular of the reactant or product. Okay, but whenever they are asking rate of appearance or rate of disappearance of that particular substance, then don't go with the stoichiometry or sign. I guess it's clear to you. Now let's proceed for the next equation. Okay, so I'm just simply writing the ROR. Okay, so if I just write the ROR, that should be here no stoichiometry, so I can write d of N2 by dt, definitely one negative sign, equals to 1 by 3 d of H2 by dt equals to, here also negative sign, plus 1 by 2 d of NH3 by dt, like that. If anyone asks, suppose like just normal one example I am showing you, rate of disappearance of H2, I have to write rate of disappearance of H2. How I should write? I have to write only d of H2 by dt. That's it. Okay, I guess it's clear to you. Okay, so yeah, let's proceed. Okay, one solve. Okay, so this is your equation. You have to find out the rate equation. See, this is in the form of average rate, delta. Okay, let me just do it for you. Let's just do it with respect to Br minus and H plus. Let me write the entire equation for you. So ROR for this reaction, it will be something like minus 1 by 5 d of Br minus by dt equals to minus d of BrO3 minus of dt equals to minus 1 by 6 d of H plus of dt equals to plus 1 by 3 d of Br2 by dt. Okay, sorry, I wrote it in the form of differential equation. Just let me correct it with the delta, right? Same thing only, just you have to replace it with delta. Delta T, here also delta, delta T, delta H plus, delta T, here also delta, delta T equals to 1 by 3 delta of H2O by delta T. This is the entire ROR, rate of reaction. Now, if you just look at the options, they are precisely choosing, specifically they are choosing Br minus and H plus. So, any two you can pick and you can equate them in order to find out your answer. Okay. So, here again I am just, all of them are equal, no, I am just picking this term and this term. Okay. So, now what it will come up? So, minus 1 by 5 delta Br by delta T equals to minus 1 by 6 delta H plus of delta T. Okay. So, this side should be empty, minus minus will be cancelled out. So, I am getting delta concentration of Br minus by delta T. Here I am getting 5 by 6 delta H plus of delta T. This is how you should figure it out. Okay. So, that's going to be C is going to be the correct answer. I guess this is clear to you. Let's proceed for the next concept, that is factors affecting the rate. Okay, so here comes the factors. First, concentration, temperature, catalyst. Whenever it comes to the matter of concentration, then definitely, if in general, it is in general study, but why I am telling in general, if there can come any kind of exception. So I really have some problem to say this term exception, because I don't feel that there is any exception in science, but you people believe in chemistry hell lot of exceptions are there. But my dear students, exceptions are said when they don't know the reason. Okay, but I feel personally that if we go deeper, then there are some reason to behave like that. So don't make any rule. Okay, yeah, IUPAC conventions are there, those are conventions. Okay, so that's the reason I always keep telling, don't make a rule like Markovnikov rule, anti-Markovnikov rule. They are just the statement. This is how the things work. Okay, but the way all the day the situations are not similar, right? Maybe every day you are going from home to your college. There are some different route as well. Maybe one day you can see the road is not good. Okay, some work is going on. So definitely you will not go to that road, right? You will just take some other route. So chemistry is also something like that. Please, my dear children, don't make a specific rule to proceed with the chemistry. Okay, and believe that, trust me guys, there is no exception. Okay, please go deeper and try to find out the reason behind it. Okay, if you are really interested in this subject. So yeah, it's my point of view that there is no exception. So again, I will not tell that exceptional cases are there, but whenever I will discuss the order of the reaction, this particular concept will be clear. But here, in what point of view they are saying? If you see A and B, they are reacting to give you product C, right? Now if you increase the reactant concentration, that is A or B, then what you should expect? Definitely the rate will be increasing. This is in general, but it may not happen so all the time. Okay, so it's an experimental fact we will discuss while discussing the order. Okay, let's proceed. Here comes the temperature. So temperature, there is no so-called exception. You can directly tell that with the increase in temperature, rate will increase. Okay, why this happens? Because definitely Arrhenius equation we will proceed well in detail, but let me just tell, while increasing the temperature, more amount of the kinetic energy of the molecule of the reacting species, they increases. They started to be colliding more, right? They started to collide more. So more collision means more product. Hence the rate increases like that. Okay, we will come well in detail later. Next, catalyst. Catalyst is an amazing thing, you know. So definitely there comes positive catalyst and negative catalyst as well. So from the childhood we are learning catalyst is something that actually enhances the rate of the reaction. Means it makes the reaction rate faster. But yes, my dear, there are some catalysts in which the rate becomes slow down. Okay, that is also positive. Those are negative catalyst, or we can call sometimes a catalyst poisoning, like that. Okay, we will go well in detail, don't worry. Okay, let's proceed. Effect of concentration. First we will proceed with the rate law and rate constant. So my dear student, rate law is very important. Definitely order and molecularity we will learn, integrated rate equation. Yes, zero and first order only we will learn, and these two are very important. If you are a board aspirant, then please learn the derivation part. I will do it here as well. For the KCET, definitely if you remember the only formula, that will be more than enough, but definitely I know you are preparing for the board as well, so I will derive it in front of you so that it helps you for the board purpose as well. Okay, next, half-life. Okay, these are the things we will cover. Okay, pseudo first order reaction, another amazing thing. Next, you can see this is a case. You can see in the chemical reaction, let's say the small A, small b, small c, small d, these are the coefficients, okay, stoichiometric coefficients, okay. So they are saying that rate is directly proportional to the concentration, okay, to the concentration of the reacting particles, okay. And what is there in the power? What is there in the power? These power x and y, these are not known. You can't tell that this x and y are always a and b. This small a and small b means the stoichiometric coefficient. No, my dear. Okay, so always like that? Always? No, my dear. If the reaction is an elementary one, elementary reaction means the reaction occurs in a single step. The reaction occurs in a single step, such as second order reaction, SN2 reaction. Okay, SN2 reaction. SN2 reaction, I guess you remember, substitution of nucleophilic, it is a second order reaction. That is a elementary reaction, single step. Okay, if the reaction is not elementary, then you can't put these stoichiometry in the power of A and B. Okay, then these powers x and y, from where it will come? It will come experimentally, my dear. It will come experimentally. Okay, so Goldberg and Wedge, these two scientists at first told that the rate is directly proportional to the concentration of the reactant raised to the power of their stoichiometry. But after few reaction, they saw that no, these things are not working for all the reaction. Okay, then they came up with the decision that it actually does not depend upon the stoichiometry for all the reaction. It only depends upon the stoichiometry for elementary reaction only. Very important. For elementary reaction, you can write A power A, B power B. But for other cases, in general, you can't write it like that. So from where the x and y it's coming? It's coming experimentally. Sometimes, let me just give you one example, right, so that you understand how experimental it's coming. Okay, so let me just see. I'm doing this reaction, I'm mixing A and B to give C plus D. Got it? Next time I'm doing reaction, keeping the concentration of B fixed, and I'm just doubling the concentration of A. Doubling the concentration of A. I saw my reaction rate got doubled. So I can tell that x power 2. X is actually 2, A power 2. Right? And B is fixed. Okay? Now what I'm doing? Again I'm doing some experiment. For this reaction. Let's say, now I'm keeping the concentration of A fixed. Okay? And I'm doubling the concentration of B. I'm doubling the concentration of B. But here I observe there is no change in rate. Yes, that also must happen. So, B power 0, Y value is 0, means rate does not depend upon B at all. Right? I guess you understood this. I'm just giving you some example. It may happen. It only depends upon the concentration of A but doesn't depend upon the concentration of B. Right? Experiment will tell you. Right? Don't ask me why. It's the nature of the reaction. This is the kinetics. We have to find out experimentally. Okay? Only it is depending upon the concentration of A, not depends upon the B. Just one example I'm telling. Okay? So, this factor, okay, that's the reason I'm telling this x and y, these terminologies are experimentally defined, and hence you can see concentration, if we increase, I'm increasing the concentration of the reactant only, right? I'm increasing the concentration of B 2 times, right? But it's not affecting the rate. That's the reason here I told you in general, okay, but experimentally it is also observed that it may not depend upon the concentration of the reactant sometimes. Okay, so B power 0, it's 0 order with respect to B. I guess it's clear now. So this is the rate law, you can just go through. Okay, and here you can see this is the rate. If you just remove this proportionality sign, then what will come? One rate constant, and that is called one constant will come, that is called rate constant. Okay, so here you can see the unit of the rate constant. Okay, I will just tell you one thing here. This x, what is x and what is y? Okay, what is x? X is basically order of reaction with respect to A. And what is y? Y is basically order of reaction with respect to B. Okay, now if I find out x plus y, okay, now it will give me, let's say, n. So n is called overall order of the reaction. Overall order of reaction. I guess now the concept is clear. If the concept is not clear related to that of the order, how the order is coming and all, then please comment me below. I will again come up with the live session, there I will clarify it. Okay, so now let me just focus on this thing, how it is coming. See, from here, what is written? Rate equals to k into a plus, a power x, b power y. Okay, let me tell you one more thing here. X, y, it can be any value. Okay, it can be positive, it can be negative, it can be 0, it can be fractional, my dear. Okay, so order of a reaction can be anything because it's experimental. It has no relation with a balanced reaction if it's not elementary, right? So order of a reaction in general, it can be anything. Okay, now this is your equation. From here, if I want to find out k is basically r divided by a power x into b power y. Okay, so here you can see a and b. I'm targeting to find out the unit. Okay, so that for the any reaction, if you see for any reaction, if you see only the unit of k, you will find out which order reaction is this. That's my target. It's a shortcut trick. Okay, so here you can see, what is the unit of rate? Rate equals to change in concentration. Change in concentration divided by change in time. Right? So change in concentration means concentration unit. What is the unit of concentration? Mole per liter. And what is the unit of time? That is second. So I can write unit of R is basically mole per liter per second. Okay, let's put the unit here. Mole per liter per second. Remember this, okay? See, I have seen people stucking with this particular thing. Unit. But trust me guys, if you know the formula, if you know how you are finding out, then calculating the unit, even if you don't remember, calculating the unit is nothing. You can see rate, I just simply calculated in front of you. So similarly, first order, second order, maybe I'm asking you -3/2 order reaction. Yes, that can also happen. As I told you, it's an experimental. Okay, -3/2 order reaction, what is a unit? You can find it out utilizing this formula. Okay, let's proceed. Divided by, see, this is both of them are concentration unit. So here I can write concentration power x plus y, right? So yes, mole per liter second inverse. Here concentration unit is mole per liter, right? X plus y, what I told, it is N, right? So from here I can do it, mole per liter, I am taking it in a single bracket. So this is going to be 1 minus N, because if this N comes up, this is power 1, right? 1 minus N, second inverse. Remember this thing, okay? So this is the thing that you have to remember, that is a unit of K, okay? So yes, if you are having second order reaction, okay, just second order reaction, just let me just take one example. How to do it, this thing, not this, sorry. Okay, so here you can see mole per liter 1 minus N, second inverse. This is my formula. Now I am asking, acha, tell me the unit of K, unit of K when the order is 4, let's say, when the order is 4. Okay, so let's simply just put the value of N as 4. So that's going to be mole per liter 1 minus 4, second inverse. So for this case you will get mole per liter 1 minus 4 means minus 3, second inverse. That's it. That is a unit of K whenever it is a fourth order reaction. So this is how you can calculate, my dear. Okay, I guess it's clear to you. Yes, let's proceed further. Okay, this is something to be solved. A rate law for the reaction is given like that. You can see the stoichiometry did not come, right? So experimental fact. Okay, now the concentration of B is doubled, keeping the concentration of A constant. Okay, so here you can see this is my normal rate. They are saying let it be my rate 1. Okay, now if I find out rate 2, whenever I am doing, keeping the concentration of A constant, okay, A is constant, 2 of B. So from here I can get 2 into K into A into B. So what is this? Don't you think that it is rate 1? So 2 into rate 1. So it will be doubled, right? So it will be doubled. I guess it is clear to you. Let's proceed. Okay, now we will discuss a little bit order, that is the sum of the power. I already told you sum of the power of the reactant in the rate law expression. Okay, so here you can see as I told you, x and y, here x plus y is the overall order. It can be anything, it can be fraction as well. Okay, so order is a very important thing. It will tell us about how the rate changes when the concentration they gets changed. Okay, the way I told you with different experimental fact, like that. Okay, I guess this thing is clear to you. Okay, that thing I wanted to remind you again. The stoichiometry will come. The stoichiometry coefficient will be the order in case of elementary reaction only. In case of elementary reaction only. Elementary reaction means single step reaction. Okay, but in case you are having a complex reaction. Complex reaction means multi-step. So definitely I will not sit to calculate the order, to calculate the rate for all the step. Okay, I will find out the slowest step. The slowest step. Okay, the slowest step is called rate determining step, RDS. Okay, the slowest step is called rate determining step. That will give me the order. I guess this is clear to you. For elementary reaction, stoichiometric coefficient can give you the order, but for complex reaction, it is a multi-step reaction. I have to find out the slowest step, that is called rate determining step, that will give me the order. I guess it's clear. Yes, let's proceed. Okay, so now we will discuss about the molecularity. Molecularity is very easy for you. Molecularity is the stoichiometry of the reactant itself. Okay, molecularity means how many moles of the reactant actually you need. How many moles of the reaction you need to proceed with the product. So here you can see 1 mole of ammonium nitrate. So molecularity is 1. For this case 2HI. So 2. Here 2 plus 1, 3. So 3. Molecularity can be obtained from the stoichiometry itself. Okay, so just go through it. This is the definition. I guess it's all clear. Let's proceed. Okay, let's proceed with this question. So which of the following statement is not correct about the order of the reaction? The first thing is the order of a reaction can be fractional number. Yes, that's true. Order of a reaction is experimentally determined quantity. That is also true. The order of a reaction is always equals to the sum of the stoichiometric coefficient of a reactant in the balanced chemical reaction. So that's not going to be true. It's true only for the elementary reaction. So yes, that's going to be the correct one. I guess it's clear. Yes, let's proceed with the integrated rate equation. So here you can see this can be 0 order and first order. These two only we will proceed with. Okay. So application, you can see, calculate how long it takes to for a reaction to proceed. This is also helps us to determine the amount of product or the reactant that is present out there, and definitely the order, to find out the order and rate constant. You can calculate out of it. Let's proceed with a 0 order reaction. So 0 order reaction means rate of the reaction is independent of the concentration. That's what I told you. Yes, there can be a possibility where the concentration of reactant will not matter to you. Okay, it will not influence the rate. Those are 0 order reaction. Okay, so here you can see this is the equation. This is the equation. A0 and A0 is the initial concentration of A is any reactant, and A is basically the, let me write it down for you. What is A? A0 is basically initial concentration of reactant A. Reactant A. And what is A? A is concentration of A at time t. Okay, so this is the like for the KCET purpose, if you simply remember this equation, it will be more than enough. Okay, but this is the curve. This is how it looks like. How you can see, this is a straight line equation. Okay, how does it come as a straight line equation? I am showing you. Okay, from here A, concentration of A can be written as minus of KT plus A0. Okay, A and R is quite similar here. Okay, so now here you can see A is your y axis, concentration of A, minus K is your slope M, T is your x axis, and this is your intercept. Right, you can see concentration of reactant y axis, time x axis. Now slope is minus K. Negative slope means it will come like this, right, negative slope, and here you can see A0 is the intercept. Okay, where the straight line touches the y axis, that is the intercept, that is your A0. I guess it's clear. So reactant versus time graph. Okay, so let me now show you how you should derive it. It's very important, 1 3-marker question you can get in the board examination. Okay, so here I will start from a reaction. Let's say A is a reactant that gives you product P. Okay, if I write rate of the reaction, then definitely minus d of A by dt, right? with respect to reactant only I wrote. From the rate law if I write, from rate law if I write, rate equals to K of A power 0, right? Because it is a zero order reaction. So let it be equation number 1, let it be equation number 2. So now I am going to equate them. Equating 1 and 2. So both of them are R, right? So both of them I can equate. K into, sorry, this 0, A power 0 means it will come 1, okay? Minus dA by dt. Something power 0 means 1. Okay, let me just a little bit arrange it. So I can write dA equals to minus K of dt. Okay, this is what I can do. Now, integrating both sides. Okay, whenever I will integrate, I will put the limit itself. So integration of d of A equals to minus K. K is a constant, so I can keep the constant outside. dt. Okay, so now I will put the limit here itself. Okay, so whenever t equals to 0 means reaction is not yet started. What is the concentration of A? A0, initial concentration. So this should be A0, right? When t equals to any random time, let it be t. What is the concentration of A? Let it be AT or normal A. You can write anything, AT. Okay. Now integration of A, integration of dA, it will give A. Putting the limit, you will get something like this. AT minus A0, sorry. Upper limit minus lower limit. AT minus A0. Okay. For this case, t equals to 0 I am not putting, it will come 0 by default, so minus of kt. So if I just adjust this sign, this here and there, it will give you kt equals to A0 minus AT, right? From here you can write k equals to, this is the equation that was given in the last slide, right? From here you can write k equals to A0 minus AT divided by t. This is the equation that can help you out to solve the numerical problem. So this derivation, if they ask, you can do it, and please don't forget to mention the abbreviation out there. What is K, what is A0, what is AT, what is T. Don't forget to mention them. I guess it's clear to you. Yeah, let's proceed. So zero order reaction, some example, the decomposition of gaseous ammonia on a hot platinum surface. Okay, one very important thing I just wanted to tell you, any kind of decomposition of a gas, if it is taking place on a metal surface, metal is playing the role of a catalyst. If it is going on a metal surface, without thinking twice, please mark it as a zero order reaction. Okay. Why I am telling you this? Because experimental fact. Okay. Now, if you just proceed with this reaction, means if I just write it like HI, 2HI will give you H2 plus I2. This is a decomposition of HI. It is a second order reaction, you know. It's a second order reaction. But same thing if I do 2HI will give you H2 plus I2. This is on a metal surface, or here you can see I am writing metal surface. On a metal surface. Experimentally it is shown that it is a zero order reaction. Remember this difference. Any reaction, any decomposition of gas, if it is taking place on a metal surface, then mark it as a zero order reaction. I guess it's clear. Let's proceed. Here one solve. Okay, a zero order reaction, A has a rate constant this. Okay, how long will it take for A's initial concentration to fall from 0.10 to 0.75 molar. Okay, let's proceed. So here we are going to apply simple formula. What was that? K equals to, just now we derived, right? A0 minus AT divided by T. T we have to find out. Everything is given. So T is basically equals to, A0 value is something 0.10, right? 0.10 minus 0.075, yes, divided by K. K value is given how much? 0.003. 0.003. Okay, just we have to calculate this much. This will come to be 0.025, right? 0.025 divided by 0.003. Okay, if I calculate this, it will come as 8 point, what is close by answer? Okay, 8.33. Okay, this much second. Okay, that's going to be the answer. So correct answer is D. I guess it's clear to you. Next, this is the first order. Okay, the rate of the reaction is proportional to the first power of the concentration of the reactant. Okay, so let's proceed. Here you can see this is the equation. I will come up with this. This is the unit of that particular, from this thing you can calculate actually mole per liter 1 minus n. This n value should be 1, right? Second inverse. Okay, if you put this n equals to 1, then 1 minus 1 0, this entire term will go 0, something power 0 means 1, right? And here only second inverse. This is how you can calculate. Okay, and okay, let's just derive this, how the integrated rate equation comes, and then we will come up with the graph as well, how these things are coming. Okay, so let's do one by one. So again I will proceed with the A gives you product. Okay, so now rate of reaction, that can be written as minus d of A dt, and this is equation 1, and from the integrated rate law I can write R equals to K into A power 1, that is your equation number 2. So equating both side, I am getting K equals to A power 1 equals to minus d of A by dt. So now same term, same side, we will do d of A by A equals to minus K into dt. Now we will do integration. Okay, so while integrating we will put the limit here. Okay, so when t equals to 0, A is A0, right? When t equals to t, any random time, A equals to AT, right? This is how you can put the limit. Okay, now see, integration of dx by x is basically ln of x, right? So same thing here, if I just put the limit as well, so ln of AT minus ln of A0, right? And here definitely I am going to get minus KT. That's it. Okay, so utilizing these also I can create the graph. Okay, using the ln value itself. See, it's a straight line equation, it's coming, but I wish to do it with respect to log. Okay, it will be even more convenient for you. Okay, let's do it. Okay, so if I take common, here you can see I can do 2.303, I can take common and I can make it log of AT minus log of A0 equals to minus KT. Okay, I can simply change the sign a little bit. Here it will come as log of A0 minus log of AT. Here it will come up to be K by 2.303 T. Okay, I am coming up with a straight line equation, I mean y equals to mx plus c. To that form I am coming, then I will again come back to that mathematical form that will help you to solve the numerical. Okay, so for this case, let's just change the sign. This I will take that side. Okay, So I will get it something like log of 80, okay, equals to minus K of 2.303 T plus log of A0. What do you think? It came up with a y equals to mx plus c. So this is your y. This minus K of 2.303, it's your m, T is your x, and this is your c. So now what I have to plot here, tell me. If I want to plot, let's say, log of concentration of reactant, log of 80, that is my y-axis, right? Log of 80 versus time graph. Time is the x-axis, right? I will get a graph like this with a slope. The slope value will be, you tell me. Slope is basically minus K by 2.303. Okay, now if you just put it here normally, okay, same type of graph you will get here, this type of graph, ln of 80 versus t wala graph, you will get same thing, but the slope you will get only minus K, right? Because you did not convert it to log, but here I have converted it to log. That's the reason slope will come up to be minus K by 2.303. Right? So remember, what is the axis? Either ln or log. Be careful about it. Log of concentration of reactant with respect to time. Okay, I guess it's clear. Now let's come up to with a form. Let's put them together. Okay, log term, let's put them together. So I can get it something like K equals to 2.303 by T log A0. From here you can get it actually, from here, A0 by 80. That's it. This is something that will help you to calculate the numerical problem. Okay, I guess I'm clear about it. Yeah, let's proceed. Okay, I guess this thing is clear to you. I already told you in this case. Here, this is the graph ln versus t. So whenever you are converting it to log, then K by 2.303 will come. Okay, and here this particular thing, just let me proceed a little bit. Log of R0 by R. Okay. Okay, what was my equation? Log of A0 minus log of 80 equals to K by 2.303 T. Right? This was the equation. Oh, okay, let me just, yeah, that will work. Okay, so now here you can see plus C. Plus C. C value, I can take it as 0. Nothing is there, means plus 0. So here I will come up to be a straight line equation. How? You can see. So log of A0 minus 80, I can write it in the form of A0 by 80. Okay, equals to K by 2.303 into T plus 0. So this entire thing is my Y. This is my M. This is my X. This is my C. Yes, let's plot them. Okay, so what is there in the y-axis? Entire this thing you have to write. Log of A0 by 80. Okay, please be careful what type of axis they are giving. Be careful about it. So here y-axis must be log of A0 by 80. And here comes time in the x-axis. So here you can see slope is positive here. So there is no intercept, 0 means it will pass through the origin, and the slope value will be K by 2.303. Okay, so this type of problem, this type of thing you can expect in your KCET level. Like if I plot log A0 by 80 versus time graph, what will be the slope value? Okay, this is how you should deal with the problem. I guess it's clear to you. Yes, let's proceed. Okay, I guess it's clear. Let's proceed now. Okay, so first order reaction, few example they have given. You can see hydrogenation of ethane. Okay, it depends upon only the concentration of ethane, not the H2. Okay, all natural or artificial radioactive decay, those are first order, and decomposition of N2O5, this is. Okay, let's solve one problem. The rate constant of decomposition of N2O5 at 320 Kelvin is this. If the initial concentration is this mole per dmq, the concentration after 800 seconds. Okay, that's gonna be super easy actually. Let's proceed. Okay, so here I will just simply apply the first order integrated rate law. 2.303 divided by K into log of A0 by 80, right? So here everything I just have to put, I have to find out 80, that's it. So 800 equals to 2.303 divided by, what is K value? 4 into 10 power minus 4, 4 into 10 power minus 4, okay, into log, what is A0? 1.6 into 10 power minus 2 divided by log of, okay, divided by 80. Fine. Now if you just make it simpler, log of 1.6 into 10 power minus 2 minus log of 80, if you do this, that will be equals to this thing, entire this thing, 800 into 4 into 10 power minus 4 divided by 2.303. Okay, now what I have to do, if you just calculate this side, okay, let me just do it. Okay, if you do this, if you just do this side, no, this will come up to be 0.14 something. Okay, now this log 1.6 into 10 power minus 2. So there is a, I am not breaking down log, I am just directly writing the calculation, but you can actually break down log. Okay, so log 1.6 plus log 10 power minus 2, like that you can do. So log 1.6 you can do 16 by 10, okay, plus log 10 power minus 2. Okay, so log 16 you can do it in the way log 2 power 4. Okay, log 2 power 4 minus log 10, and here it will come up to be minus 2. So this is our log 2 value. If you put here log 2 value 0.3, right, power 4, log 10 1 minus 2, if you calculate like this you will get it. Okay, so once you will get it, the value comes up to be something like minus 1.79. okay, minus log of 80 equals to 0.14. okay, so now minus log of 80, if I just take this term there, it will come up something like 1.79 plus 14, right, it will come up to be 1.93. okay, now if you have to do anti-log. So how I should do anti-log, that also I am telling you the trick. 10 power, sorry, $80 is basically equals to 10 power minus 1.93. You can just take 1.9 as a simple value. So how you should get minus 2 minus 0.1, like that you can do. 10 power 0.1 value you have to remember, then you can just put it over there and you can get the value easily. Okay, so if you just simply calculate this, it will come something like 0.0117. okay, from there you can write 1.1 into 10 power minus 2. So this is going to be the correct answer. Okay, you have to break it, I guess you understood. You have to break it like 10 power minus I'm taking outside 2 minus 0.1. Okay, this is how you can proceed. Okay, then if you just simply break it down, na, you will get it 10 power minus 2 minus plus 0.1. From there you can write 10 power minus 2 into 10 power 0.1. 10 power 0.1 comes up to be something like 1.1. Okay, so you can simply break it down like this and you can proceed. Okay, I guess you understood. See, it's not the problem solving, I'm also telling you the trick, so please don't forget to write them down. Okay, let's proceed. This is the half-life. I'm not showing the half-life further. So any kind of half-life, any order reaction, you can just apply this formula, a power n minus 1. Okay, so now for the zero order and the first order, this is the formula for the zero order reaction, A0 by 2K. The half-life actually depends upon the concentration of A for zero order, but for the first order it doesn't depend. The formula comes up to be 0.693 by K. I'm not coming to the derivation because it's not actually relevant for the second PU board as well. Let's proceed. Remember the formula, by the way, that will help you. Okay, a first order reaction is 50% completed in 1.26 into 10 power 14 second. How much time would it take for 100% completion? Okay, let me tell you, my dear, first order reaction, it never gets completed. Okay, because some exponential term comes over there, because you can see ln term came out there, right? Okay, so if you take it from that side to the opposite side, it will come up to be E exponential. Okay, so that's the reason it is said that first order reaction takes infinite time to be finished. Okay, so don't proceed further, just mark it as infinite. Okay, it never gets completed, first order reaction. Let's proceed. Here comes the pseudo first order reaction. So pseudo first order reaction, this is a first order reaction but actually a second order reaction. It appears to be a first order reaction. Okay, so like when it happens, whenever one of the reactant is more in concentration, okay, than other reactant. Okay, so like we can just take the example of inversion of cane sugar, we can take the example of, you know, hydrolysis of ester, this type of thing. So pseudo first order reaction is one of the most important question for the second PU, and for your KCET level the examples are very important. Okay, inversion of cane sugar, you can take the example of hydrolysis of ester. Okay, these two are enough. Okay, now methods to determine the order. Graphical method, it can be initial rate method, integrated rate law, half-life method. Okay, let's see one by one. Let's solve this type of problem. You can see, you can directly tell me, if you're just looking at the graph, you can now tell me what type of reaction is this. It is passing through the origin, C value is 0. What type of reaction? Yes, it's a first order reaction. We just did it, right? Next you can see this type of thing, whenever you will be having a sort of datas. Okay, so here you have to make the equations. You have to make the equations so that you can find out the value of x and y. X and y is going to give you the order. If you just normally write rate equals to k of a power x b power y. My target is to find out x and y, right? So let me write these three equation. Okay, rate value is said as 0.10. Here K, concentration of A, they are saying 0.30 power X, B value is 0.30 power Y. This is equation number 1. Okay, next 0.40 equals to K into 0.30 power X, 0.60 power Y. This is my equation number 2. Another one, 0.20 equals to K into 0.60 power X into 0.30 power Y. This is your equation 3. I guess it's clear. Now I have to divide or multiply the equation in such a way, division you have to do actually. You have to divide the equations in such a way so that I can get the value of x and y. You have to check so that the similar term gets cancelled out. Okay, so what I am going to do here, let's do 3 divided by 1. We can do it. Okay, so if I do first 3 equation 3 divided by 1. See, everything will be cancelled out, right? So 0.20 divided by 0.10 equals to k into here 0.60 power x into 0.30 power y divided by k into 0.30 power x into 0.30 power y. Okay, see, everything will be cancelled out. From here I am getting, this is 2, from here 2 power x, if you cancel out this thing. Okay, so as a result of this I can take x equals to 1 if you compare, right? Again same thing I will do here. Let's do 2 divided by 1. 2 divided by 1 if you do, then I will get something like 0.40 divided by 0.10 equals to k into 0.30 power x into 0.60 power y divided by k into 0.30 power x into 0.30 power y. So here you can see, if I cancel out, it will come as 4. This will cancel, this will come up to be 2 power y. So from here I can write 2 squared equals to 2 power y. From here I can write y equals to 2. So let's put this thing in the first equation. So rate is going to be something like a power x value is 1 there, right, and b power 2, right? So option B is going to be the correct one. I guess it's clear to you. Let's proceed. This is your initial rate method. Okay, let's proceed. Okay, now we will finally proceed with the effect of temperature. Okay, it's very important. For a chemical reaction with rise in temperature by 10 degrees Celsius, reactant constant is nearly gets double, and this is called reaction coefficient. Okay, so that you don't have to focus that much, but more precisely we will focus on the Arrhenius equation, okay, and Boltzmann distribution curve. So Arrhenius equation, the formula is very important for the board level, because the numerical problem also comes out of this, and also they ask directly write down the Arrhenius equation and mention the abbreviation. Okay, so the temperature dependency of the rate constant, that can be well explained in the Arrhenius equation. This is the equation, k equals to a into e power minus a by RT. Okay, so this is the graph that I need to explain you. Okay, so for this case, as you can see, first we will see H2 plus I2 they are reacting, H2 plus I2 they are reacting, and they will come up to 2HI, right? So in general, reactant concentration should be like, let me just take it different curve. Okay, here let me explain one thing. Okay, in general, what should be the case? Reactant is more stable or product is more stable? So definitely reactant is less stable than that of the product in general. Why this is? Because if the reactant is stable, then why it will go towards product? Right? Why it will go towards product? But so in general, if the reaction is occurring spontaneously, you can tell that the reactant is less stable than that of the product. Okay, so I am marking the reactant here, random reactant and product. This is reactant, this is product. Okay, so now if you just see how the reactant to product conversion is taking place, like this. No, my dear, it could go like this, but it doesn't go like that. It actually takes this pathway. It covers a hill station in between. Why this hill station? Why this much? Because bond breaking, existing bond breaking of the reactant and bond making, it requires some sort of energy. That's the reason it must proceed through a energy barrier, energy gap, and this energy gap here at the peak there exists a state that is called transition state. Okay, so whenever it is in the transition state, it is neither reactant nor product, something in between. Okay, and this energy that is required for this, it is called energy of activation. Okay, and this case, whenever it is neither reactant nor product, it's very unstable case, right? That's why it is energetically so high, means so unstable. Once it reaches activation energy, then coming back to the product is very simple, right? Okay, so this particular case, here you can see, let it be my enthalpy 1, this particular case. Okay, let it be enthalpy value is H2. Okay, so now if I want to find out the reaction enthalpy change, okay, it should be final minus initial, H2 minus H1, right? So now final minus initial, now here you can see H2 is less than that of H1, right? H2 is less than that of H1, H1 value is more, right? So as a result of this, here negative comes more, overall the things will come as negative, enthalpy value comes negative. Okay, and in this type of reaction you will observe that the energy is released. It is an exothermic reaction curve. Okay, it happens by default, but it releases energy. That's the reason exothermic reaction enthalpy value comes negative. I guess it's clear. Now same thing I will do for the another case. This is the reaction coordinate. Now let's say reactant is stable. Reactant is stable, and here comes the product. So reactant is stable, so definitely you have to push some energy, you have to give some energy to push the reaction. So definitely it's an endothermic case, right? Here by default the reaction was taking place, and at the end of the day you are getting some energy, that is exothermic, but here you have to give energy, right? Otherwise why the reactant will react? It is stable. So from here again the same thing, it has to cause the energy barrier. Here comes the transition state, let it be H2, let it be H1. This is the activation energy barrier, right? So now for this case, what will happen? Delta H again is basically H2 minus H1, but here H2 is greater than H1, right? And hence the value will come up to be positive, that is the endothermic phenomenon. I guess these things are clear. Why endothermic positive and why exothermic is negative? I guess this is clear to you. Okay, let's get back. So now easily you will just understand this curve. This is activated complex or the transition state. It is the same thing only. Okay, so yes, let's proceed. Okay, so now if you just take log both side, if you take ln, in fact if you take ln both side, so definitely this thing is going to change, right? This thing will not be E anymore, it will be ln of A minus EA by RT, ln of A minus EA by RT, that's going to be your equation. Okay, now if you just take two such equation, K1 and K2, you will get two different T value as well, T1 and T2, and then if you merge them, if you add them or if you subtract them, these two equation, you will get the Arrhenius equation that actually we use for the numerical purpose. We'll come up with it. So for this case you can see ln of K, this is my y axis, okay, and this particular thing EA minus EA by R, minus EA by R, this is your M, and 1 by T is your X, right? And ln of A is your C, y equals to mx plus c. So here you can see I will get ln k versus 1 by t graph. 1 by t is your x. Okay, now slope, if you just see minus a by rt, so slope should, the straight line should be like that. So slope is basically minus a by r, and intercept you can see ln of a. I guess it's clear to you, straight line graph. Okay, in case you are having these two with respect to 2K and 2T, I am not deriving it, it's not needed for your board as well as for the KCET purpose. Just remember here only just one I am taking K1, another equation I can take it as K2, and here also T1 and T2. Subtract them, you will get back to this equation actually. Okay, so I guess it's clear to you. This is the equation that will help me to proceed with the numerical problem. Okay, that definitely I will solve a few of those numericals in the live session in front of you. So now we will proceed with the Boltzmann curve. Okay, very beautiful things. So Maxwell-Boltzmann, they did research on the kinetics, and they said the fraction of molecule, only those fraction of molecule will give you the product if they are having the activation energy. Okay, so once they will cover this activation energy, or you can call it as most probable energy, then only they can give you the product. Means this side they will not be able to give the product. This side, whenever they will cross this side, they can give you the product. Okay, now here you can see they did the particular research in two different temperature. So first temperature, if you just see, okay, first temperature, if you see, if you are having only T, this is my T at temperature T, so the graph is coming like this. So only this much amount, you can see this gray coloration, this dark gray coloration, only this much molecule will give you the product. But whenever you are making the temperature T plus 10, now the graph gives you this much area. So look at the area enlarges. The area, now it was this, now it is this much, right? Initially it was this much, now it is this much after rising the temperature by 10, right? So this area means these many fraction of molecules get added to this, right? So that's the reason it is proven that whenever you are increasing the temperature, fraction of molecule that covers the energy of activation gap, it will be more. Okay, that is a Maxwell-Boltzmann curve. I guess it's clear to you now, right? Let's proceed. Effect of catalyst, it's very important actually. Okay, let me just show you normally here. Again, let's say reactant product. It will just cross this much Hill station. Here I am having activated complex or transition state, and the difference in between them is activation energy. Okay, now just tell me, crossing over a hill station is easier or taking a way through a tunnel is easier? So let me just make a way for you through the tunnel, right? Now look at the activation of energy. Look at the energy here. It's lesser than that of this, right? Catalyst plays the role like this only. Okay, it creates the tunnel in between the hill station. Okay, as a result of this, the activation energy gets lowered and the reaction can take place faster. Okay. So here you can see the graph, this is the graph that I just explained. So reactant in general, it will follow this path, but in presence of activation energy, the path will be altered. As a result of this, there will be a decrease in activation energy, right? So effect of catalyst, it's very important for you. If you are a board aspirant, then please go through this in detail. You can get a 3-mark question out of it. I guess it's clear. So what is the role of activation energy? I mean, what is the role of catalyst? Positive catalyst, it decreases the activation energy and hence increases the rate. Okay. So I guess it's clear. Now we will proceed with a collision theory a little bit. Collision theory, people thinks it very, very hectic. Okay, so let me just make it very simple to you at first. Okay, so whenever you just first day, let's say it's a very first day in your college. Okay, so you will meet so many people. So with all of you, will you talk? No, you will find a certain group of friends with whom you can match the vibe, right? So first important thing is vibe match, right? Now in some cases you like someone, Okay, now in those group of friend only you got someone very, you know, special. Okay, you know it better than me actually. So in those particular case, what will happen? Okay, so for that particular person, it is more prominent. It means, yeah, vibes are matched with all the friends group, but with that particular person, I'm getting some connection, heart-to-heart connection. Okay, fine, everything is fine. You got a vibes match as well as heart-to-heart connection. Now, if that person is not taking you for a date, if that person is not giving you samosa, if that person is not giving you chocolates, then because he is not getting enough pocket money, another fact, then this will not exist, right? So this is in general case, please take it as in a generalized version, just giving you example. So what are the important thing? First is vibe match, second is that connection, proper way of approach, that way I can tell his approach is your favorite, like that. And next is money to go for a date, right? So for these three conditions are similar to proceed for a reaction as well. Just imagine how lively those molecules are. Okay, the way you people think, molecules also think in the same way, and that is the collision theory. First, as I told you, you meet so many people, right, whenever you will go to the college, right? So similar thing, in a container, A and B reactants, so many reactants are there. So A and B will face so many molecules. Collision will take place, right? Collision will take place. So many collision, random collision will take place, right? But collision is important, right? So if you made a group of friend with the same vibe, collision, right? Next, effective collision. Next is effective collision and orientation match. Orientation match is that correct way to approach heart-to-heart connection. How? Let's say if I'm taking the example of SN2 reaction. In SN2 reaction, we always say backside attack. From the backside, the nucleophile should approach. If the nucleophile should approach in the front side, no reaction at all. The nucleophile must approach from the backside. When they are colliding, maybe effective collision, but that approach is not good. So that particular person, when it is approaching in a proper way, right, heart-to-heart connection, right, for the SN2 as well, whenever the backside approach is there, only that cases the reaction is taking place. So first, nucleophile and reactant colliding, but not effective collision. Effective collision is happening, vibe match, okay. Now, approach, orientation. So orientation barrier is now done, backside approach, fine. But next, you are going for a date, you need money, right? So that transition state, backside approach is there, everything is fine, but it's not having that much energy to create that activated complex or the transition state, activation energy, right? So this is the collision theory. You need three sets of condition. First is effective collision. Next one is orientation barrier. You have to cover the orientation barrier. Next, what you have to proceed? You have to have, you must have that energy of activation so that you can break the old bond and you can form a new bond, right? That is a collision theory. Here you can see this theory, we will just consider the molecule to be a hard sphere and they keep colliding each other, and here comes few terminologies. You can see the number of collisions per second unit volume. Okay, let me tell you, my dear, as I told you, you meet so many people, right? So every day in your college also you will meet so many people. So in the same way, in a second, in a cubic centimeter, in a cc volume, there can occur 10 power 27 collision in a second, but all of them are not effective, right? So if it was the case, if this many collisions are going on, just you are giving the reactant and you are getting the product, just you are giving the reactant and you are getting the product, this doesn't happen, right? So effective collision is important. All the collisions are not effective, right? Okay, so another factor which affects the rate of the chemical reaction, that is the activation energy. So whenever the collision theory, they will ask you about like what are the factors that can like hamper a reaction rate in accordance to the collision theory. You can just take the name of effective collision, next you can take the name of orientation barrier, and finally activation energy. Okay, so this is the way you can write the rate as well, where Z is called the collision frequency in between A and B molecule. Okay, so you can see orientation I already told you. So this is the, you know, say SN2 wala reaction. This is the improper orientation. If OH minus approaches from the front side, there will be no product, but if OH minus approaches from the back side, nicely product will be formed. Okay, so these are the things that you have to remember for the collision theory. That's it. Okay, so here this is the thing, here P is called another thing that is called effective collision. So effective collision, collision frequency into activation energy term. Okay, so 3 terms you have to remember. What is, first is effective collision, next is collision frequency, next is activation energy. That's it. Okay, I guess this is clear, and here we are ending up with our one-shot video. I guess you enjoyed, you understood your chemical kinetics chapter. So please make sure you had been through the entire video up to the end. You are making a proper note, and please don't forget to comment me below if you are having any doubt. And in the meantime, don't forget to like, share and subscribe this particular channel if you have not done yet. So yes, thank you so much, and we will come up with the live session on this particular chapter very quick. Thank you so much.